Yeah, hello, good morning. My name is Sir Kelvin, as you've heard, and this is our game theory block course. Now, game theory was invented back in the 40s of the last century. Morgenstern, for example, was one of those guys who actually brought it on the way, and the reason why it happened at that time is the Americans wanted to win the war, which they finally did, right? Now, this course is not about winning the war. This war is about escaping traffic jams and crowd disasters, right? So game theory can be used actually for many different things, and it's one of the most powerful quantitative theories of social behavior. I'll start a little bit with self-organized traffic flows. Having mentioned congestion, this is what happens every day. And it's happening because above a certain critical density, people respond with a delay to slight changes in the speeds of the car ahead. And so basically that leads to overreactions. The driver will brake a little bit harder, and then we have a chain reaction, so the next driver brakes even harder, and so on, that finally cars get to stop, even though no driver wants this to happen. So we call this systemic instability. Many of the unsolved problems of the world are based on systemic instability, including many disasters, stock market crashes, and so on. So this is very important to realize. Even if you have the very best intention, that may not be enough to produce the outcome that you want to produce. Even if everyone has the best intentions. You don't need to have an evil mind to produce that traffic jam. Now, in order to avoid traffic jams, we've built traffic control centers. But I'll show you that we can solve the problem also in a decentralized way. We don't need to have the big leader who tells us what to do. We just need to have coordination mechanisms. In order to develop those solutions, we have started to model traffic flow. So we first need to understand what's going on. At the moment, there is again a discussion about the strategy of ETH, and basically says, don't do fundamental research, despite it ends up with applied products, and services or something like that. So traffic is just okay. So we have to model it. There is an equation of motion. So the location changes according to speed, but how does the speed change? And here basically vehicles respond to the car in front, and what matters is the relative velocity, the distance, and also the own velocity, because it enters the safety distance. And yes, this is one of the models that has been used extensively to model traffic flows, and this is what you get. A surprising variety of different kinds of traffic patterns, all self-organized based on the interactions between the cars. We could say a zoo of congestion patterns. Very surprising at the time. And then the next thing that you want to do is you want to understand when do you get what. And that brings us basically to so-called phase diagrams, right? What we see here is the flow on the freeway upstream of an on-ramp where vehicles enter. This is the flow of vehicles entering. We call it the bottleneck strength because those vehicles take away some capacity. The sum of both flows is the overall traffic volume downstream of the on-ramp where vehicles enter. And so if you go from here to there, basically traffic flow increases. That's why we have free flow over here and congestion over there. But you can see with the different colors, different areas where different things happen. Moreover, you see that things depend on the size of the perturbation in the traffic flow. If the truck overtakes another truck, basically what happens is that this produces a large perturbation, and as a result, you're in this situation. So we have history dependence, we have multi-stability, so different kinds of things can happen depending on initial conditions, depending on history. Hysteresis for those who study physics and so on. All of this is happening in social systems and traffic systems, highly exciting, but in this case, unfortunately, we don't like traffic jams, apart from theoretical investigations, which are very interesting. We would like to get rid of them all, And so how do we do that? Well, basically, we have understood that the capacity of a street drops when congestion sets in. And so basically, we need to avoid that congestion sets in the first place. Because once you have congestion, you'll have it for a long time because your street cannot serve so many vehicles any longer. The capacity is then given by the number of vehicles that can leave the traffic jam in front of the traffic jam. And there are delays because drivers respond to each other with delays, right? Now what we've done is we have introduced adaptive cruise control systems in real cars, by the way, that would accelerate and decelerate for the driver based on measurements from radar sensors that measure the distance and relative velocity, so they would automatically drive the car, slightly different from what people do. So we've changed the interaction mechanism. That's called mechanism design. So in that model that I mentioned before, the intelligent driver model, there were a number of parameters. A, acceleration, B, deceleration, T is relative distance, time gap actually. And so we will change those parameters by certain factors in certain kind of situations. In free traffic, we just stay with the normal parameters, but if we approach the end of congestion, we want to avoid accidents, so basically we want to be on the safe side and brake a little bit more. And we have the congestion itself. Most of the time the vehicle just behaves in a normal case, but when it comes to the front of the congestion, it has to accelerate quickly, so A is being increased over here, as you can see, and the time gets slightly increased, reduced in order to get more capacity. The combination of that produces more capacity and stable flow, and this way we can actually dissolve those terrible stop-and-go waves. Right? So this is now a visualization of a model as I have explained it to you, and it shows you that we can understand the stop-and-go traffic. Now we saw the on-ramp where vehicles are getting in, disturbing the traffic flow, which is then being amplified. It produces stop-and-go traffic, and then we switch on the traffic assistance system where cars drive automatically. And even though the same number of vehicles still enter the freeway, you see that now the traffic jam has disappeared. It's gone. So by changing the interactions, we change the outcome of self-organization. And we can get all sorts of outcomes. So we need to understand what kind of interaction causes what kind of outcomes in order to produce the outcome that we want to have. Automatically, by self-organization, like magic. Yes?
Is such a model valid until a certain threshold, where is there a moment where there are happen, or is this model valid for any amount of?
No, of course there are limitations as long as cars have a finite size.
Yeah.
But the point is really basically to compensate for bottlenecks along the freeway in order to avoid traffic flow breaking down. And you can see over here, really this is quite effective. That would be the traffic jam if we don't do anything, if we introduce just 10% of cars with the adaptive cruise control, that would largely reduce the traffic jam already. 20% would almost make it disappear. So the interesting point is we don't have to equip all the vehicles with that technology, and it already has collective beneficial effects. And now basically we want to do the same thing in society. Get rid of the problems in a way that's not painful at all. In a way that doesn't tell anyone, you have to do this, and you have to do that, you know, like with the control center. And that it just all happened wonderfully like magic by understanding how self-organization works, you know. Now we have to go back, of course, to Auguste Comte, who was basically the father of sociology. Actually, in the beginning, he called his field social physics. And he had this vision that sociology would be the queen of sciences. You know. Who thinks sociology is the queen of sciences? I kind of expected this. The point was, and here he's right, social systems are among the most complex systems that we know. And at that time he, yes?
It's also the king and the dictator, and like, I think if you take all these, I think sociology being the queen, I think is not so wrong.
At that time he imagined that sociology would make the same phenomenal progress as physics did. Physics did experiments basically and understood the interactions between the different components. Sociology didn't make that progress also because of lack of takedown for a long time. And now the question is, will computational social science deliver the breakthroughs? Because now there is big data. And that, of course, is very interesting for you because you are born into a completely different kind of situation, and you could make the breakthroughs. So you might turn sociology into the queen of sciences one day. You know? We're working on it. But there's big disagreement about how models in sociology should look like. Some people think, you know, a model should describe every single detail of human behavior, including how you respond to this blink in the eye of a person, you know, which may cause you fall in love or whatever, you know, all those details. And others think, you know, we want to understand the essence. If you have a lot of parameters, we can basically produce any outcome. Some people say with 3 parameters you can fit an elephant, with 4 parameters you can make it wiggle with its tail, you know, and with 5, 10 or 20 or 100 parameters it would do anything, you know. So how can we understand anything if we have so many parameters? So they say, okay, boil it down to the essence and come up with simple models that grasp the essence and allows you to understand this essence of what really causes certain kind of phenomena. And this battle is ongoing, you know, and some people say, okay, simple models obviously are wrong because they don't catch any all the details of the system, but focus on certain kind of phenomena. You know, these are these kind of people, and they say, okay, just add in new knowledge on top of what we know and put it all into one model, and others say, like Josh Epstein, if you didn't grow it, you didn't explain it, and he means if you didn't come up with a model that allows you to simulate it in a computer, you cannot be sure you understood what is going on. And he wrote wonderful books, and latest one, I think it's Agent Zero, so have a look at this book, because it's a book you can learn a lot from. Now, social scientists want to understand a lot of different kinds of phenomena, including homophily. That means the fact that similar people flock together and agglomerate, social influence, coordination, cooperation, group identity, social norms, social differentiation, social structure, deviance, social exchange, conflicts, and we'll probably come up with even more things. And how should we understand this? Well, basically, we want to go at least one level below the phenomenon we want to understand. We want to start with elementary assumptions. That we shouldn't put in what we want to get out. What we want to understand should be an emergent phenomenon. So we should put in elementary stuff like birth, death, competition, perception, memory, mobility, these kind of things, And of course, we cannot do it all in 60 minutes. I have to disappoint you here, but we can do a little bit of it, right? And we'll focus on competition and mobility. When I came here to ETH Search, I saw, so over time we would come up with models for many of those phenomena, and the question was, what kind of models would it be? And we decided, let's make a game theoretical approach. Game theory is a mathematical discipline providing a set of analytical tools and solution concepts which have explanatory and predictive power in interactive decision situations when the goals and preferences of the participating players are potentially in conflict. I mentioned Morgenstern. The other famous author is John von Neumann, and he is really an astounding scientist because he made contributions to quantum physics. He made contributions to the architecture of computers that we still use. And he invented game theory together with Morgenstern. And just if you want to be ambitious in life, that could be kind of a person to orient it, Okay. And we will focus in particular on evolutionary game theory. That means a dynamic version of it. We want to understand how certain kinds of behaviors, in their frequency of occurrence, change over time in the population. That's the relative probability of finding a certain behavior I. And so people could change from behavior I to behavior I prime. There would be transition rates that we need to specify. And they could change from some other behavior I prime to behavior I. And so basically the change of frequency of a behavior is given by inflow into I minus outflow from I. And then we have to specify transition rates. Here we have to make assumptions. And we basically would assume there is a certain easiness to change from I to I prime, depending on what kind of behaviors we're talking about. Now, quit smoking is probably more difficult, so kind of transition rate would be smaller, and it would be a prefactor or post-factor in this case. And here we would have spontaneous transitions, imitation processes, and avoidance processes. And imitation is basically proportional to the number of people who show that behavior that we would imitate. In the following, we'll focus on imitation. Why? Because this is so important in social communities. People do imitate. That's a quick way of learning. You don't have to start from scratch, and that's why you're basically coming to universities, to not only do everything from scratch, but also to learn from others, right? So that's imitation. So if we just focus on imitation and assume that there is a certain expected success of a behavior that's given by the payoff if behavior I meets behavior I prime. So assume we interact, I show behavior I, you show behavior I prime. That's the payoff, Heinrich talked about payoff matrices. That's kind of the essence, the core of game theory. And then this is the relative frequency with which we have to multiply this to get the expected success, and basically we could assume that we're more likely to change if the expected success of the other behavior that we would assume is higher. And if we expect that our success would decrease, we wouldn't change our behavior, would we? Okay, so you put it all into the previous equation, you get this equation, and it's called Replicator Equation, but at the same time it's the evolutionary game theoretical equation. The Replicator Equation comes from evolutionary theory in biology, where you have mutation and selection, and here we have imitation, and also a kind of selection because you want to do better, right? So you choose. All right. And then you could plug in all sorts of payoff matrices, and we'll focus on a few. Now, let's have a look at pedestrians, right? What I personally find particularly interesting is that if many pedestrians interact, we'll find interesting collective patterns of motion by self-organization, such as this, like if people walk in a corridor, basically you will find those lanes of uniform working direction that separate from each other and produces an efficient way of motion. You don't need a policeman here, you don't need traffic signs here, you don't need laws telling people what they should do. If you would stop those people and ask them, what have you done? They would not even have realized that they have actually formed those lanes, that they were part of a collective behavior. It just happens. And the question, why does it happen? Now, first of all, the point is the relative velocity of people who walk into opposite direction is larger than the relative velocity of people who walk into the same direction. So oppositely walking people meet more frequently, and when they meet, they have to step aside, and that separates them. And you don't need to assume a certain preference for one side for this to happen. Lanes would happen anyway, just because of this higher relative velocity of opposite moving people. But there is also, on top of this, a preference for one side. So there are basically behavioral conventions. And how can we understand this? So for example, in Europe, most people tend to walk on the right-hand side. In Japan, most people tend to walk on the left-hand side. So it's not given, like as a physiological thing or something, right? So it's an outcome of the social process. And the game we're confronted with over here, it's called coordination game. So assume two pedestrians, right? They want to pass each other. And they have two possibilities, either go to the right or go to the left. If both people go to the left, then they successfully pass each other, and so that has a benefit. If both people go to the right, that also works well. They again have a benefit. If one goes right, one goes left, they are still standing in front of each other. No success, no payoff. So that is the payoff matrix of the coordination game. Now we plug it in to the replicator equation. So here are the details basically, and what we end up with is this equation over here. And then we look at it and say, oh, interesting. First thing we do is, what are the stationary solutions? I mean, put this to 0, and we would find something that would be stationary over time. There's 3 possible solutions. Which ones? Do you see them? Come on. Nobel Prize waiting for you. Not this time, 50-50. Half of them going to the right, half of them going to the left. 100%, everyone going to the right, and 0, everyone going to the left. These are the 3 stationary solutions. And then you would make a stability analysis, as mathematicians or physicists would say, and you figure out that this 50-50 situation is unstable. Those other 2 solutions are stable. So what happens is we may start like on day 1 of society with 50-50. Like 50% go to the right, 50% go to the left. But then, it slightly varies from day to day. Just by accident, by coincidence, whatever, And then you get away from this solution because it's unstable, and you get into one of those solutions, and it will stabilize. And there you have the behavioral convention. And it's stabilized for the right-hand side in Europe, and for the left-hand side in Japan. So we can all understand that. But we don't only want to understand the avoidance behavior. You want to understand pedestrian behavior more generally. So the question is, can we do that? Some people think people just behave randomly, and so how can we make models? They could do anything. Yeah, maybe they could, but are we doing anything, No, we're quite efficient in many cases, We don't want to lose time if we are not maybe exploring the environment like a tourist. But let's say, you want to walk from the tram station to your classroom, and so why should you lose time? You don't want to have collisions, and so you have many of those interactions with other pedestrians, and you learn what works and what doesn't work, Children, for example, often make mistakes and run into other people. But eventually they learn that maybe not a good idea. And so they learn how to walk around other people, and they learn to do that in a more and more efficient way. And then in the end, there is an efficient way of doing it, and there is a mathematics describing this efficient way of doing it. And we have come up with a social force model to approximate that behavior that people would eventually learn. So there's an equation of motion for pedestrian alpha. Again, the speed determines change of location in time, and then the question is, how does speed change in time? That means we need an acceleration equation, and here we assume that we could approximate the acceleration as a superposition of forces, where we have a driving force that describes the adaptation of the actual velocity to a desired velocity and desired direction of motion, and it takes some time, relaxation time, and then there are interactions, repulsive interactions in many cases, and there would be interactions with boundaries, streets, walls, and so on, also typically repulsive, and there could also be attractive interactions if you walk with your friends, or if you walk in a tourist group, so you could put all of this in. You could also add a random force, because people don't behave in a deterministic way. Yeah, and here basically we do that a little bit in more detail, and then the question is, how exactly would the interactions between pedestrians look like, the repulsive forces that we have just assumed. And one could make different kind of assumptions, like a circular kind of repulsion law, an elliptical one. It could take into account the size of the step of the pedestrian, the so-called stride, and so on. All of those specifications, however, can derive the interaction force as a gradient of a potential function. Physicists study this, it doesn't have to be real, but it could be a good approximation. And the question is, how good is this approximation? So you need data, but first of all, I'd like to say these kind of models are also part of game theory. So-called differential games. And basically there's a Lagrangian formulation as we know it from mechanics. And you may remember that basically the laws of mechanics could be understood as optimal behavior according to a certain kind of Lagrangian function, right? Same thing for pedestrians. And then, in fact, yes, let's look into data. And it all started with camera technology that allowed to determine trajectories of people. We're not interested in faces. We don't want to know who they are. We just want to extract the space-time lines. Right? And then basically what you have to do is you have to compare the prediction of your simulation model with what actually happens. So for each pedestrian, you want to predict where will it be in a second's time. And there will be a prediction by your simulation model, and there will be the actual position given those other pedestrians around and how they move. And so basically you determine the error, you add up the errors, and you try to find the parameters that would minimize those errors, and you would say these are the parameters determining pedestrian behavior. Right? So you would take a number of assumed models, determine from the empirical data the optimal parameters, and then see how much error is there still left. And that model with the smallest error, you would say that's the best model that we know of as of now. And you can do that for the circular, for the elliptical, and so on. And you can also add some kind of vision effect. People don't respond so much to what happens behind them because they don't see it. And so we could add in, so elliptical too was best, by the way. And it turns out kind of the strength of the interaction decays with distance in an exponential way. That was actually the first assumption that we had, but later on we learned that that worked the best. And here we're now taking account an additional prefactor to this force in order to take into account the field of vision effect, and that's this formula over here, and that's what we actually find in a model-free kind of approach. Okay, so that were early attempts to determine the forces between pedestrians. When we started off, we didn't have data at all. We had to make assumptions. And those assumptions produced the lane formation phenomenon. We said, oh, that's interesting. Many people found that interesting. It's one of the most cited papers in interdisciplinary physics, by the way. And later on, there were data, and we were fitting models that we assumed. And then we were trying to determine the models themselves from the data. That means you need even more data to do that. right? So eventually you get towards a data-driven kind of approach. And in order to produce the data, you need to make experiments. So you invite a lot of students in order to make these walking experiments. You put table tennis balls on their shoulders so you can track the motion in very much detail. You can see that's kind of going up and down because there's kind of stepwise motion, and all of that can be tracked. And then here you see the exponential acceleration, so it fits human behavior quite well. And then you start have people interact with each other, men and women standing and walking and all of this, and you do that hundreds of times. It takes a lot of time to do those experiments and quite a bit of money and sophistication, but eventually you have quite a bit of data, statistical data, so that basically describes what happens depending on where this other person you interact with is located. And one of the things that you find is that there's an asymmetry in the side choice behavior. If one of the pedestrians is standing, the other one is just walking around, that asymmetry is small. If both are walking, then suddenly you have really a large preference for one side. That means there is a reinforcement effect. People respond to each other. So if there's a little bit of preference for one side, and if two people have a little bit of preference, then kind of that not only adds up, but there's kind of a multiplicative effect, you could say. Yes, and so you could really determine the force field from the data and then try to map this on mathematical functions. And this model over here basically determined that there were two components. One is when you are just in front of another pedestrian, you would start decelerating in order to reduce the relative speed and avoid collisions. If you're a little bit to the side, then you would change direction. Of course, you would do that anyway, but kind of there wouldn't be so much deceleration, but there would be more directional change effect. Yes, and so basically you can write up the entire model that has been extracted from the data, and then you can compare the experimental data with simulation data of the model that has been fitted to the data, and then you find that there's a quite okay fit of the real trajectories with the simulation, through the simulation trajectories, and in particular the mean values match quite well. You see also standard deviations over here. We can also understand that asymmetry of the avoidance behavior. So besides trying to reproduce the measured data of individual interactions, we have made another validation. Basically, we took video recordings from a pedestrian zone, where a lot of pedestrians, not just two, were walking and interacting with each other, and so we were simulating this based on the model that was calibrated with two people interaction. It was not calibrated to that particular setting over here. As you can see, there was a very nice fit also of that much more complex collective setting found in real life rather than the experimental setting. Okay, and then you have a reasonably good model and can start to simulate interactions of many pedestrians, and what you find is that eventually you will have lanes of uniform walking direction. Now we have, I think, about 4. I might reduce to 3 and eventually 2 of them. But there's clearly a lane formation phenomenon, right? And you would also look into other kinds of situations, such as bottlenecks. And here something interesting happens. will find oscillations of the direction. So, people are pushing to get through the door, but one side basically manages to pass the door. On the other side, people have to wait. More and more people will be accumulating. The pressure will grow. That pressure will stop the other flow. And this way, this pressure model can explain the turning of directions. This looks like there is a traffic light, but there's none. There's also no policeman. There is no one who tells people how to do that. It just happens by self-realization, right?
But is it efficient? It doesn't look very nice.
Wow, that
It looks accurate, but it doesn't look very nice. It says that they're really pushing, right? They're not. They don't seem to be polite.
I mean, the goal of that simulation is to understand those naturally appearing oscillations, right? It doesn't say that you should throw away all the traffic lights. But on the other hand, I'd like to point out, which is not part of my lecture today, we have used this observation in order to invent a new kind of traffic light control, where the traffic flows would control the traffic lights rather than the other way around. And that turns out to be more efficient than the traffic control center approach that I mentioned in the beginning. So kind of having people steer traffic lights that they then respond to again, that would be the most efficient thing. And now there's also an interesting phenomenon with two streams of pedestrians trying to cross each other. True. Yeah? Now just assume there are kind of thousands of people walking across this way. I want to walk this way towards you, So basically all those people, they would be almost like a wall to me. But if I had 1,000 people behind me, and basically both streams would try to move forward, then eventually we would find this stripe formation phenomenon. And this is really amazing because it allows people to cross the other stream without even stopping. And how does it work? Well, basically, you walk within such a stripe. You walk forward with the stripe, you walk sidewards within the stripe, and this is how it works. So once you have the self-optimization of the stripes, that does the job for you, basically. It's a generalization of the lane formation phenomenon, right? Yeah, and eventually you could say, what about cognitive features of people, don't we have to take this into account as well? And of course, we should. And in the beginning we saw if we add cognitive features, that would make models extremely complicated. There would be dozens, if not hundreds of parameters. But now it turns out actually that you can come up with cognitive heuristics that would describe pedestrian walking behavior and respond to other people well with very few parameters. And basically two rules. Walk into the least obstructed direction and hunt for gaps along your way. And then adjust the speed to keep a certain time headway. That's it, And that's why you don't have to think much about walking, It just happens. Once you know the trick, once you have learned it, you do that just on the side. Yes, and then again, you can ask, can we apply that? And of course, people are kind of evaluating buildings, optimizing buildings, and you have, for example, to make sure that people would not get stuck here at the corners because everyone wants to cut the corner. Kind of the most simple models wouldn't work well here. You would want to be able to simulate complex environments with many rooms and with corridors, and you would want to simulate even more complex situations with many levels, evacuation scenarios where people would have to find the staircase and walk down the staircase and all these kind of things, and you would have to model route choice, because if you just assume local interactions, then basically what happens is that in this situation there's of course a bottleneck, and more people would queue up at the bottleneck, even though there is an alternative way. But they realize it only once this crowd is really big, you know. Still nobody realized that there's another way. But now eventually one person noticed that other people are following too. You know, this needs to be better in a computer simulation, because real people are typically not that stupid, right? And so here is an improved simulation that adds in a route choice model, which doesn't only respond to distances, kind of tries to minimize distance, but tries to minimize walking time, and thereby takes into account congestion, right? And you see this now works pretty well. Yes?
Have you added any imitation with this one? Because I think that once you see a
Yeah.
stream of people going somewhere, you would be very likely to imitate them.
No, we don't have imitation in that model. It's really based just on the walking times. I think I'm mentioning imitation later on. Okay, and then you could also ask, can I make simulations of really huge scenarios? And the answer is yes, and can simulate thousands, even millions of people, but then you probably need to have a supercomputer and need to do multi-core processing, and we did these kind of things. And then you can simulate complex settings where people are basically leaving the subway, then they walk, then they catch the bus or tram, or take a car or whatever, and maybe you want to add in logistics too. So in the meantime, these kind of models are being used really for simulators that are being used for architectural planning, for urban planning, for the planning of events, for the study of evacuation scenarios. So here's just an example. We'll fill this festival area. Of course, the filling process is not usually the issue. The issue is, can you get this area evacuated within a short time if there is a threat? And then you could also take into account interaction with the environment. So if people walk on grass, that will trample the grass, and it will make it easier for other people to use the same path. It will reinforce the path, and eventually we'll have trail formation. And it turns out that because of that trail formation, that existing trails are attractive. People wouldn't always take the shortest path, but they would make compromises basically, because just here you can see it, for example, or here you can see it. So then the question is, can we understand that? And yes, we have also created models in order to simulate this kind of phenomena. And then you could look at a situation where you have 4 entry and exit points. People want to go from here to there, and they want to go from here to there in a diagonal way from here to there, and so on. And now assume that this area is not walked through frequently, so the grass can grow back. And there's a competition between the growing of the grass and the use of those trails. And there are not enough people to maintain all those direct connections. What happens then is they will form trails that are compromises. because then people who walk from here to there, people from here to there, and people from here to there would all use this part of the trail. So you have a higher usage frequency that can maintain the trails, right? Now the interesting point is what comes out of this is a trail system that produces a fair detour for everyone. Everyone over here is about 22% of detour. No matter whether you want to go from here to there or from here to there. 20 to 30% of detour seems to be okay for most people, but not more. Same with Texas, I guess. So, and you can see that's why people don't like T-shaped intersections, but they would prefer the Y-shaped ones. And there are some architects who have understood that and have put that into practice. But not always things work out well, unfortunately. Sometimes you might have crowd disasters. If there are too many people in a constrained space, so you wouldn't get the lane formation. The lanes might break down, and you would have a crowd disaster, as we saw it at the Love Parade, for example. I don't want to play the movie; it's really terrible. And unfortunately, crowd disasters have happened many times in the past decades, again and again, and it's about time to avoid these kind of disasters. It should be updated. I don't know why it doesn't work. So these are a couple of examples in South Africa, in Brussels, the Heysel Stadium. That was in Sheffield. That was in Brussels. So all over Europe we had crowd disasters, and we have seen crowd disasters also in nightclubs, where people basically try to escape through the staircase and then fall on top of each other and don't manage to get out of the falling crowd and suffocate, basically, so they don't get enough oxygen anymore, and that's how they die. So then the question is, why do crowd disasters happen if nobody wants to harm anybody else? No, people don't want to kill other people here, right? That's what we should assume, I guess. And so we have started to do simulations in order to understand that better. And so we have assumed people would get nervous in difficult situations. For example, if you see a fire or a situation is smoky. So the typical lane formation phenomenon that we have seen before, which happens over here, wouldn't necessarily occur. Instead, you might have a situation where we get what we call freezing by heating. The fluctuations and nervousness, the noise breaks up the lanes, and you could get blocks of people confronting each other, so they wouldn't be able to move forward. Yeah, such a confrontation also happened in the Love Parade disaster in Duisburg. You could have a fire and smoke might impair the vision to an extent that you don't even see your own hand in front of your eyes anymore. If you get into such a situation, you usually get down to the floor because the smoke goes up. Smoke is also poisonous. It would affect your entire body system and your perception and so on. Poison you. So go down on the floor and try to escape. Here we have assumed there would be several exits, but we also assume that people would tend to follow others. That's the imitation effect, right? I mean, we're interested in how much imitation is good to evacuate efficiently and how much imitation is bad. You know? Because if everyone runs to the same door, the other door is not being used, and obviously that's not efficient at all. So a little bit of imitation, but also some exploration, some trial and error behavior. That combination might be good, as we actually see over here, right? So we also made experiments with people, or we blindfolded them, put something in front of their eyes, and they had to evacuate a room, and then if they do it alone, then basically they're trying to get to the wall, and then they walk along the wall until they find the exit, right? And sometimes they're lucky, and sometimes they're unlucky. If there are many people in a smoky room, then you would find this kind of situation. So while if they have full visibility, of course, everyone just goes right away to the exit. In a smoky kind of situation, things are much more complicated, and some would follow others, some would take their own paths. And then the question, can we improve pedestrian facilities so evacuation would be more successful, more people would survive, hopefully everyone, of course. And here is a surprising discovery. If too many people push at the narrow door, then basically you could get a clogging effect. People would impede each other. And so it's difficult for them to get out. And here it says, experiment, we'll see not only is there a tendency to fall, but also in between the outflow stops. Now, if we put an obstacle in the way, I don't know, there should be a... okay, good. The outflow becomes more smooth because it basically avoids that everyone is pushing towards the back of the people at the door. So it's taking away the pressure from your back. And therefore you don't have the clogging effect, and that's why with an obstacle you could have a higher outflow. The Romans already knew about crowd disasters, they had the Colosseum full of exits, and everyone was entering through the exit that they should take. There were up to 73,000 visitors, 76 enumerated exits. One of the world wonders. Have a look at it when you're in Rome. So the question, can we improve pedestrian facilities? And they are made up basically from corridors, bottlenecks, and intersections, right? And all of them are designed the wrong way. It's easy to understand for the bottleneck situation. If you cut away those corners, you get a funnel-shaped design, and that works better. Everyone can understand that. But once you have understood this case, and basically you say, oh, less can be more, kind of taking away space can be beneficial. And so why don't we put some obstacles into the way here in the corridor? And it turns out, actually, this is helping to separate different flow directions. Seeing people coming towards us now, another metro line is arriving, and after some time, basically, people towards us are on the left-hand side, and people walking to the opposite direction on the right-hand side. Those pillars are a flexible design that help to help the crowd to self-organize itself. Now, what can we do at intersections? And here we observed another puzzling thing. If we put an obstacle into the center, it improved the efficiency. Why is this? Well, basically, there are several kinds of self-organization phenomena that can occur, collective patterns of motion. One of them would be a circular, anti-clockwise flow. Or it could be a clockwise circular flow. Or there could be a situation where you have oscillations, where for some time people in those directions can walk and the others have to wait for some time, and then those would walk and the others would have to wait. And of course you can imagine none of those patterns is stable, there's a competition between these patterns, and so that ends up with a chaotic dynamics basically in the intersection area, and you don't want this. You want to select one of those collective patterns of motion, so if you do this, then basically you stabilize counterclockwise flow. It also considers that people tend to walk on the right-hand side. So that's how you could make things more efficient. Now, remember, what happened when we had two crossing flows? We had stripe formation would happen, potentially. Not so if you have four intersecting flows, you get chaotic dynamics. So why don't we split up the intersection of four walking directions into four intersections of two walking directions? And this is exactly what we do over here. It's kind of just another way of presenting what I just showed you before. And then you have the stripe formation over here, and that stripe formation over there, and so on. And all together you have a circular flow, right? If you do it the wrong way, then you mess up the flow even more, right? So you need to understand the pattern. Well, that would be kind of the variation of that one. Yeah, so this is the way of making flows more efficient in intersection areas, right? And in fact, there have been experiments with quite dramatic improvements of the pedestrian flows, right? And now the question is, couldn't you perhaps optimize architectures even automatically? And the answer is yes. You know, just take the success principle of evolution, and so start with a certain kind of architecture, and then multiply that architecture and vary it randomly. That means apply some mutations and then do some test runs with computer simulations, evaluate those test runs according to certain performance criteria, then select the best versions, multiply them again, go through the cycle many times until you have more efficient solutions. And this is what happens if you start with a room that has a narrow corridor as an exit, right? So because of the mutation, you get some curious bad designs for some time, but eventually what you get is this funnel-shaped design with a convex funnel that obviously works much better. And you can do that also by, in a different way, where you basically drop mini obstacles and let them aggregate, and eventually what you would see is that you would find either zigzag-shaped or funnel-shaped design where the funnel is asymmetric. And why is this? Because if those many people push, then that creates like slogging effect. People don't efficiently get out of the room. If you do this, then the walls are absorbing a lot of pressure from the people pushing behind, and that frees up the people at the exit, and they can walk through the exit nicely. So we could potentially improve the design of stadia in such ways, you know, by using zigzag designs. Also have the diameter grow with the number of rows of people who want to get into that corridor, like in a river where more and more water flows in and gets bigger, right? So that would be the natural design for pedestrian flows. And you may have heard that the Muslim pilgrimage in Mecca was struck by many crowd disasters in the past. One of the areas where many crowd disasters happened was the Jamra bridge close to Mecca in Mina. And this is how it looked like for a long time, the old Jamra bridge. And so there are basically three pillars that represent the temptation by the devil, and so you have to throw small pebbles, small stones at the pillars to kind of show that you resist the temptation by the devil. But that makes the situation very crowded over here, and sometimes that caused crowd disasters. In one year, January 2006, a crowd disaster happened here in the open area. The size of this on-ramp is a two-level structure. That's why it's called a bridge. I think it's 40 meters, and that is 80 meters if I remember well. So hard to imagine for most people that this is not enough capacity. But there are 3 million people in a day. And if you look into the flow, what happened is there was a camera, and the camera's recordings were evaluated, and turns out that people here merged, two different flow directions merged, and that was enough to create a bottleneck. And what happened is free flow turned into stop and go flow. Which we already know from the clogging effect, actually, right? So that's a simulation of the evacuation from a room where everyone's pushing. We have this clogging effect. Sometimes nobody gets out, and it takes time until the next people get out, and so on, right? So that's kind of the problem. And then not only do you have the transition from laminar to stop and go, but finally there's the transition to what we call crowd turbulence, where people are being pushed around into all possible directions when the density is very high. You're squeezed in other bodies, basically. And this is where crowd turbulence starts, and people may be pushed over large distances, may fall to the ground, other people may fall on top of them, and that is what causes the crowd disaster. So, terrible situation that needs to be avoided. And yes, there have been improvements suggested that have been quite effective. I haven't been involved in this for many years, but things altogether improved dramatically. Now other people are taking care of this for many years. Okay, so I think this is a good point to stop. I just maybe want to add that similar stuff like mutation in selection also occurs in other models of human behavior. So we were interested, for example, in the evolution of Homo socialis, as I call it. It means of social preferences of people. Usually it's being claimed that we're selfish because if we were friendly and would give other people some of our resources, they would have more kids, we would have less, and so the nice people would have less kids, and those we give something would have more kids, and so basically the bad guys, kind of selfish people, would spread, and the friendly people would eventually disappear. And it's been believed for a long time, and we have simulated that in a computer, where we have assumed people have a certain utility function where they give a certain weight to the utility function of other people. I mean, how well they're doing. And the way we're giving to the success of other people is called friendliness. And we start a simulation where the friendliness is 0 in the beginning for everyone. But eventually, through mutation in selection, this is what happens. oh yes, Homo economicus can result and will result for many situations, but this. In this corner over here, you find the evolution of Homo socialis with other regarding preferences. And this happens when children are grown up close to their parents, which is what people do. Now, most animals leave the nest after a very short time. Kids would stay with their parents for, say, 20 years. That makes a hell lot of difference, it turns out. And takes a number of generations, dozens of generations, in fact, for this transition from selfishness to other regardedness to happen. But eventually it happens. So even if everyone starts to be selfish, unfriendly as hell, eventually you would find this distribution of friendliness where people kind of give a weight of, say, about 40% to the well-being of others. It's almost like love your neighbor as yourself. It's interesting. And in fact, if you look into the real behavior of people, yes, there are some selfish people, but most people have pro-social preferences, actually. And also, that was known already to Adam Smith, who said, however selfish man may be supposed, there are evidently some principles in his nature which interest him in the fortune of others and render their happiness necessary to him, though he derives nothing from it. And that has been forgotten by many economists for a long time. And on the long run, this is what will happen, basically. Even if we start selfish, there's a true population of selfish people, red and orange. As you can see over here, over time they would become other regarding and cooperative, and they would mix, even though they're different tribes. So we can learn to cooperate throughout the world. I hope that will soon happen. But it requires a new paradigm in economics to model this, and it needs new institutions to support this kind of behavior so the good guys wouldn't be exploited. And digital assistants can be actually tools to get there. Reputation systems can be one of those mechanisms that can help protect cooperative people, make cooperators interact with cooperators. We can build social technology that supports win-win situations, avoids situations where people would suffer from losses. And so, through technology, through new kind of social interaction, we can turn social dilemma situations, say a prisoner's dilemma, into something else where cooperation can thrive, and this is where we want to go. Thank you. Any further questions or comments? Oh yes, maybe start over here.
We saw earlier that a corridor that is zigzag-shaped improves the flow of people. Could it also be that that is the reason why rivers tends to flow in a curved nature?
That has a lot to do with fluid dynamics and the interaction with sand, say. And there's a very nice paper by Albert Einstein, by the way. What didn't he do? About exactly this meandering of rivers. So maybe you want to have a look at this. Yes. So here the interaction with the environment plays a role, for the rivers, right? Where in our case, the architecture didn't respond to the people. In the case of rivers, that happens. Yeah. So there was another, yes, please.
You mentioned the metro system before, and I realized in Japan they have these arrows on the floor guiding people in Tokyo and the metro. Do you know anything about that? Is it like research related or something?
In Japan, this is very efficient because trains really stop where they say they stop, and the doors will be where the doors are shown to be. You know, this is really amazing. And people respond to these signs because they know this is the most efficient way of getting in and out the train. We don't have so reliable stopping of trains, and all the time the numbering of the wagons is changing, you know, and so basically, so far Europe couldn't implement that, but maybe one day we'll learn it. I can say though that also in Switzerland they're trying to experiment with a number of measures. So the station in Bern is suffering a lot from crowding and opposite flows, people who are kind of almost panicking, trying to catch their train that leaves in 2 minutes or something like that. So they're trying to reshape the corridors in such a way that they would support flow direction. We'll see how well that works. Yes?
So I think that a lot of times people don't think how other people will react to what they're going to do. For example, you have all these bottleneck situations. It's because of that, right? They're pushing because they don't say, okay, now you go in, then I go in. But sometimes they just, like, I don't know, you're walking to a station and then you have people stopping in the middle of the corridor to, I don't know, to tie their shoelaces or to pick up their phone or anything. So I think that maybe along with design, what do you think, how could we make people think about the consequences of their actions? Because I think, so it's like the cars, right? In the cars, in the first example, implementing this digital thing, this is what it's doing, right? It steers how a human would behave.
Right. So it's a matter of exercise. You would certainly realize that in big cities, people would stand on escalators on the right, while in smaller cities that doesn't happen. So in big cities, things are sorted out after some time, it seems. Whereas people who take educational measures.
So they didn't have enough.
Now, a lot of pedestrian infrastructure has become less efficient because now people have their smartphones in front of their faces, don't see other people, don't respond to them properly. So we would need more capacity. And where do we get that capacity? We would have to rebuild everything. So eventually we might end up with so-called mixed reality. So basically, while you're looking into your smartphone, we tell you now left, now right. Pay attention. Yeah. That's a likely thing to happen. Yeah. Yes.
In your slide, there's a process, iterative process, multiplication, and then mutation, and then you show example of how we obtain a better design of the bottleneck. I don't understand why we are like, are we guaranteed to converge to that unique solution?
Well, you were asking whether there could be multi-stability and it could be different kinds
or
of...
might it diverge?
I don't think the divergence problem would be most likely occurring here. It more tends to occur kind of in learning problems. If you have kind of a supercomputer that applies machine learning to figure out how society, every one of us behaves, and we have these parallel social interaction networks, that would lead to very bad convergence or maybe no convergence at all, Well, I don't see why we would have this kind of problem over here, but it could still be that there could be multi-stability. That means you would get different improved designs potentially. You could also get stuck in a local minimum or a local optimum. That means there could be even better solutions, but you get basically caught in a particular kind of solution, and then you would have to add some noise in order to figure out whether that is really the best one or not. But there's a big literature on evolutionary algorithms, genetic algorithms, and all this, and algorithms and swarm algorithms, and couldn't talk much about it, but yeah, there's a hell lot of interesting stuff out there, and that is also something that you can apply to game theoretical problems.
So in that iterative process, we're basically adjust the parameters in our models, right? Based on the results.
You can apply this kind of method to adjust parameters. You can apply it to adjust architectures. You know, you can apply to have pedestrians learn certain kind of behavior. So you may add some cognitive features to pedestrians and some learning abilities. So there's many interesting things that you can do. Yeah, thanks. It was a lot of fun having this lecture with you. So I hope you enjoyed the blog course altogether.